Hi everybody, so in this video we're going to take a look at the first law of thermodynamics, sometimes known as the law of conservation of energy. So for energy we're going to write it as the letter E, and we'll talk about changes in energy. So for a change in energy we're going to use this Greek letter delta, and that usually means that we're going to have some final value after we've done something to the system, and that'll be relative to the energy of some initial value. So we start with some amount of energy, E sub I, that's initial, and we add some heat or do some work, and we end up with some final state of energy, maybe higher, maybe lower, and then this delta E is simply that difference. And I've already given away the parts of delta E. We have Q, which is heat, and W, which is work. So this represents heat, and this represents work. Now, in chemistry and in geochemistry, we make work positive. In some cases, in engineering textbooks, you'll see this equation written differently, where it will be Q minus W, and that only means they're looking at work a little bit differently than the way we do in chemistry. With engineers, they want to build compressors or other kinds of machines that do work, so when something does work, that's a positive thing. But when a system does work, it expends energy. So in their system, when it does this positive thing, the total energy of the system is decreased. For us, we're going to look at the case where positive work means work is done to the system, so it increases the energy. So it's just a matter of the sign that we put on work. Do we make it positive or do we make it negative? So it's really kind of arbitrary. So just in case you see this, it doesn't mean that the equation has been written incorrectly. It just means it's been written by an engineer. So we'll just kind of ignore that. So let's erase the chalkboard and come back to our equation here. So delta E is equal to Q plus W, heat plus work. Work is probably the easiest one to attack, so we'll do that one first. Work is equal to force times a displacement. So we'll just write displacement as D. But we can also rewrite force as a pressure. So pressure is some force divided by area. If we rearrange that, solving for force, we could say that force is equal to a pressure times area. So we've just taken this equation here and rewritten it like this. Let's take this concept of force and put it in over here. That means we would have work is equal to pressure times area times distance. And then if we take area times distance, we can combine those two. If we have some area and we multiply it through some distance, we get a volume. So we can think of work as pressure times some change in volume. So this is called, sometimes it's called PDV work, because instead of delta, where we have a finite difference, we'll use dV, where it's an infinitesimal change in volume. But anyway, we'll clear the chalkboard again and just rewrite this with our new term. So delta E, the internal energy in a system, is equal to Q plus PDV, where PDV is our way of expressing work. Well, we can think of pressure colloquially as a force. It's a type of force, a force normalized by area. And then delta V here, or actually we don't want the dV, we're using delta notation here. We need to preserve the delta notation there. So let's make that a delta. This is a displacement with respect to volume. So there's a force that acts on the system, and that force causes the volume of the system to change. So you have a little cylinder here, we apply a force, and now it's a shorter cylinder. So that's our displacement, the change in volume that's accompanied with applying that force. Well, we can apply the same concept over here, where we can think of heat as equal to some force multiplied by a displacement of some sort. So what would be these forces or these displacements? Well, let's say we had some really hot material here. We'll draw a cube. And let's say next to that, we have some very cold material. Let's draw another cube right next to this, and we'll draw it in blue to show it as something that is cold. So we have hot next to cold. So there is going to be a transfer of heat. So heat itself is not really temperature per se. Temperature is the force. So next to this red cube, we'll draw a large T to represent a large force. And this guy has a smaller T to represent a smaller force. And so we're going to have temperature, a temperature force pushing in this direction. So we could think of temperature as a force, and the displacement that's going to occur are going to be with the atoms that are sitting within inside these cubes. These atoms are going to move around with a certain velocity, and they'll have a certain amount of order, or rather disorder. And so the way we think about heat, or Q, is that it is equal to a force. In this case, that force is temperature, and the displacement in question is what we call entropy. So delta S, this is entropy. And entropy is a measure of disorder. There is entropy that is related to the vibrations of the atoms. So as we go from hot to cold materials, if we just take a look at these atoms here sitting in that cold box, as we move heat from the red box to the cold ones, the vibrations will increase, so that's one kind of displacement. And then another kind of displacement is with respect to order. So it has these at least two different components that we can think about with respect to entropy. So to just summarize this then, for our first law, we can write it like this. The change in energy of the system is related to the heat, which is T times delta S, plus the work, which is P times delta V. So that's the Q plus W. Heat transferred in or out of the system, and then work done to or by the system. If the work is done to the system, this is positive and the energy gets increased. And then if the work is done by the system, then energy would decrease. By the same token, we can have temperature acting as a force in a way that increases the amount of entropy, and that would be a heating up of the system, so Q would be positive. Or temperature could act as a force that decreases the entropy, where we draw heat out of the system, we slow down the vibrations, and maybe increase a little bit of the ordering. And we'll come back to both of these comments in a different video.